Question 8 is a challenge. With solving for 3 different temperature values, ambiguous wording, and different solutions being potentially correct, it requires a tactical solution path. The challenge doesn't just lie in knowing the engineering or interpreting confusing statements, but in revising your work with the multiple choice possibilities. Initial critical thought solution elements. 1. What are you solving for? The entering and exiting dry bulb and wet bulb temperatures for air flowing through a coil. 2. What is the fundamental process? Total heat transfer for air and adiabatic mixing of moist air streams. 3. What are the first considerations to find the solution in connection to the fundamental process? Finding where the air is mixing and where the heat transfer is occurring. 4. Are there key assumptions? Sea level altitude, standard air, adiabatic mixing, and steady flow energy transfer. And a critical assumption, common flow paths for an air handling system. The first thing to notice when solving this problem is the available answers. All options give 55 degrees dry bulb as the exiting temperature. This is clear in the question. Under common circumstances, the air leaving the coil is the supply air. Refer to the NCEES Mechanical Reference Handbook, Section 9.3.1 for proof. Supply air is the air flowing directly into the conditioned space. So from an initial reading of the question, set up a diagram like this. Solve for air temperatures entering here and exiting here. The question gives the supply airflow rate. The question gives air temperatures for this conditioned space. And it says there's heat gain inside this space. Finally, the question gives outdoor air temperature, and it says it's ventilating the room at a certain flow rate. Notice nothing is said about return air. The information leaves an incomplete picture. You must make assumptions to complete the picture, and then check your assumptions against the possible answer choices. Without any specific information, assume standard and common conditions. Again, refer to the Reference Handbook, Section 9.3.1, to see what's considered standard and common. There's obviously air flowing into the room, so air must also flow out. The conditioned space isn't being pressurized. This outflowing air is return air. It returns from the room to go back through the air conditioning process. So, the airflow circuit looks like this. The conditions of the air here in the return leg must be the same as the conditions in the room, because nothing has been done to it. It simply flowed out of the room. The next piece of the puzzle is determining how the outside air fits into this schematic. This is perhaps the most difficult issue with the whole question. It says that outdoor air is ventilating the room. What does that mean exactly for this circumstance? Does it mean this is an exotic configuration and the outdoor air is directly coming into the room, like this? If that's the case, then the temperature of the air entering the coil is exactly the same as what's in the room. Look up the room conditions on a sea level psychrometric chart. The intersection of 78 degrees dry bulb with 45% RH gives a wet bulb temperature of 63.5 degrees. Now, check the possible answer choices. Option A gives 3 out of the 4 temperatures. You just have to solve for the exiting air wet bulb temperature. How tempting to think that 3 out of 4 is enough, and to select option A and move on to the next problem. To solve for the exiting wet bulb temperature, you need to do a mixed air calculation and a heat gain calculation for inside the room. The outside air and the supply air mix inside the room, and their resulting mixture causes the heat gain inside the room. This means a solution path for determining air masses and enthalpies, connecting them to heat gain, and then using that information to find wet bulb temperature. Beginning with the room. A mixed air calculation must be done to determine the enthalpy contributed by the two incoming air streams. You can't just add the enthalpies in a total heat gain equation like this. The total heat gain must be attributed to both the air streams combined, so combine the air streams CFM. But that means the enthalpy must be between these values, not the sum of these values. Total combined heat gain and total combined airflow means the mixing of streams creates an enthalpy somewhere in between the supply air and the outside air. Mixed air calculations always require masses of the air streams. Use the equations found in the NCEES Mechanical Reference Handbook, Section 9.2.3, which you should have memorized. Find supply air mass flow with this equation. From the psychrometric chart, look up outside air and room air volumes. Outside air at 92 degrees Fahrenheit dry bulb, 76 degrees Fahrenheit wet bulb equals roughly 14.26. Room air at 78 degrees Fahrenheit dry bulb, 45% RH equals roughly 13.75. Outside air mass flow is 700 CFM times 1 over 14.26 equal to 49.01. Room air mass flow is 700 plus 3600 CFM times 1 over 13.75 equal to 312.73. Therefore, 49.01 plus the supply air mass flow is equal to 312.73, and the supply air mass flow equals 263.72. Now find supply air enthalpy with this equation. From the psychrometric chart, look up outside air and room air enthalpies. Outside air at 92 degrees Fahrenheit dry bulb, 76 degrees Fahrenheit wet bulb equals roughly 39.6 BTU per pound. Room air at 78 degrees Fahrenheit dry bulb, 45% RH equals roughly 28.6 BTU per pound. Therefore, 49.01 times 39.6 plus 263.72 times supply air enthalpy equals 312.73 times 28.6. Supply air enthalpy is equal to 26.56 BTU per pound. From the psychrometric chart, find the intersection of 55 degrees Fahrenheit dry bulb with 26.6 BTU per pound. Wait, it doesn't exist. You can't determine the wet bulb temperature using the outside air flowing directly into the conditioned room. Option A in the multiple choice is impossible. All this work based on what the word ventilation might mean. Now let's find the correct solution. This video is brought to you by ExOverZero, which offers the best PE study tools possible. To purchase our practice exams, use the link below. You're left with the assumption that the air handling schematic must look like this. The outside air and the return air mix before entering the coil. You've looked up all the relevant data for the outside and room air in the dead-end attempt just shown. Also, remember that the room air conditions are the same as the return air conditions. Do the mixed air calculation for the incoming air here. Notice there's a difference from before when allocating the CFM. Now the supply air of 3600 CFM must equal outside air of 700 CFM plus return air. Return air mass flow is 3600 minus 700 CFM times 1 over 13.75, equal to 210.91. 49.01 plus 210.91 equals the entering mass flow, which is equal to 259.92. Determine the mixed air dry bulb temperature using these masses. Don't use CFM, even though the NCEES solution does. It's a dangerous approximation method that can be wrong at times. See question 57 for an example of this trap. Using mass always gets it right. You should have the mixed air dry bulb temperature equation memorized. See the ExOverZero video on question 7 for a full explanation of this equation. 78 plus 49.01 over 259.92 times 92 minus 78 equals 80.64 degrees dry bulb. Since so much time was spent finding out that option A is wrong, take a tactical approach now to save time. The only option available for an 80.64 degrees dry bulb entering temperature is option B, which is the correct answer. You should select it and move on to the next question. To see how the other variables are answered, the mixed air temperature is always on a straight line connecting the two input streams. On the psychrometric chart, draw a straight line from the outside air of 92 degrees Fahrenheit dry bulb, 76 degrees Fahrenheit wet bulb, to the return air of 78 degrees Fahrenheit dry bulb, 45% RH. Where that line intersects with the mixed air temp of 80.64 dry bulb, find the wet bulb temperature. It's roughly 66.2 degrees Fahrenheit wet bulb. So entering air is roughly 80.6 dry bulb, 66.2 wet bulb. For the exiting air wet bulb temperature, use the total heat equation for the gains in the room. When given sensible heat and latent heat gains, the calculation is for total heat gain. For more about this, study ASHRAE Fundamentals, Chapter 18, Equations 7 through 10, which are found under the subtitle Heat Gain Calculations Using Standard Air Values. Remember, the coil's exiting air is the supply air. The total heat equation, which should be memorized, is applied to the room's heat gain like this. Use the room enthalpy value you already got from the dead end option earlier. 90,000 plus 40,000 equals 3,600 times 4.5 times 28.6 minus supply enthalpy. Supply enthalpy is equal to 20.6 BTU per pound. On the psychrometric chart, look up the intersection of 55 degrees dry bulb and 20.6 BTUs per pound. Wet bulb is roughly 51.8 degrees. To get good at questions like this, study ASHRAE Fundamentals Chapter 1, Section 10, Typical Air Conditioning Processes. In the ExOverZero practice tests, do problems Test 1, number 10, Test 2, number 9, Test 3, number 9, Test 4, number 10.